So I used to work at TripActions and Travelbird before as a data scientist, building data products in an organization. So taking care of your models as you ship them is something that I have suffered from to a certain extent. I used to do research before that, but I kind of got into coding quite a lot for during that research, and I thought maybe I should get paid for that rather than get paid for writing grants that you never get and you have to move around to research a topic that usually nobody cares for. So that's a little bit about me. So actually, I'll start with a sort of like cautionary tale. I don't know if you've heard of Zillow. It's a U.S. company that was using ML quite heavily for quite a lot of their, let's say, decision making or even automated decision making. So it happened that okay, I have to like turn and move this microphone a little bit so I can. I mean, actually, I should look at this, but it's a bit far. Um, Actually, I'll just do that. So it turns out that in Q3 and 4 of 2021, Zillow ended up estimating by over $500 million the price of the value of houses to purchase. So this kind of like led them to quite significant losses, as written here, and they even had to fire a bunch of people because they had made so many bad decisions. Um, so this coincided actually with a strong sort of change in market housing conditions that caused the prices to fall. Their models had been trained on market that was going up. So there is kind of probably quite a lot of strong evidence around here is that they kind of like used their models. The models were very good. They believed in them, and they kind of let them to decay. So before we go into like bashing a company for doing that, that's not the aim of the talk, right? Did they do everything badly? No, actually, they did a lot of really standard stuff that you would do. They trained their models rigorously. That's always a word that hurts me. During testing and development, right? They did that. They then released their models gradually. Usually like tracking a bunch of KPIs, making sure that it plays well, and then scale it up and serve it to more and more, and eventually you start believing in that model, and you're like, yeah, good, let's take into account this input. um, so the typical sort of life cycle of you've got a bunch of very clever data scientists working on a model. They do all their goodness, they put it to prod, and Bob's your uncle, you're making profit. So any good data scientist team would actually do all of these steps. That's and they do, right, in general. Um, but could it have been avoided? Most likely, yes. So obviously, we know that stuff in nature changes. All right, that's just the reality of things. And since we generally try to model some natural or artificial or some phenomenon, things change, and therefore, and also, pricing is definitely one that changes quite significantly. So this common pattern causes what we generally refer to as data drift or concept drift, label drift, all of these drift relatives. We'll talk a little bit about this. But basically, what happens is something changes in between the moment you trained your model and later. And any good data science team is aware of that, like very much. But generally, there's no time for slapping yet another piece of code or infra that sort of maintains and checks all of these things that will change in the future. Sometimes you don't necessarily know which ones will change in the future, so you kind of would end up having to verify all of your input features over time, build kind of a bunch of code and all that. The bold claim of this is that really it isn't so much the core job of a data science team. Like there was a talk this morning that talked about it was the GPU talk where data scientists are really busy at the top of level. They're busy, making a model that works well, understanding the domain problem, building the stuff that the predictions are good. Do they want to necessarily have to slap a bunch of code to perform validations? Well, probably that's usually something that ends up like on your backlog. And as we know, all things that end up on the backlog go to die. So it's actually not an uncommon thing, right? And I think every data team at some point probably ran into this. It maybe didn't bit them in the ass so much as it did for Zillow, but or the impact of the decision model was maybe less crucial. But we've all been there if we've put some model into prod, unless you use something, or you've got a modern data stack and you have all of the stuff that allows you to also apply data validation kind of as an easy extra small step. So really, this, the thing that I want to convince about, that was the sort of subtitle of this talk, is like, it's important to think about data quality, and probably a very good idea to use a framework that allows you to do this. And we've heard about a lot of them today. So, but just before we go into this a little bit, I'll just take a detour into data drift, just in case anyone is still unsure what I mean with this. It'll be very high level. It's the end of the day. It's not necessary to go too much into the maths of it. But here are two examples. You have, I don't know how to do the thingy here. Yeah, where you go. So here, let's imagine it's fake data that I generated using a normal distribution. In real life, things don't look like this, but for today, they will. And we have here like distribution of some order prices, right? Maybe something that you would put in, let's say a linear regression, because we're going to keep it simple today, to predict some decision. It could be buy or not buy, or is a valid order or not, or predict some time series, and whatever. This is the state of the data as you train it, right? You train your model, and maybe you've learned to do something. If it's above the mean, then some decision will come up. If it's below, some decision will, come down, or something like that. Let's, keep it to a simple example even there. You train this, you've got your model, it works, you've, sort of tested that it works in practice with a bunch of real data, all of that stuff. You've, deployed your model, and it's all fun. And then, later on down the line, something changes about an order price. It could be because the underlying nature of things have changed. It could be you have a problem in your transformation. You've just added some business logic that's faulty or whatever. And you end up with a system that in the future looks maybe a little shifted. So this is just, I took a normal distribution again with a mean of 650, and here I have this plot. So really, what is data drift is basically, at least when we call, and this is about features, right? So like stuff that you would put into your model to get a prediction out of it. It happens when the distribution of one or more of your input features is changed between, for example, the training time and the deployment time, or at time n in the life cycle of your model. This happens to features. It can happen to labels as well, or it can happen to the predictions that come out of your model. So literally, you could look at drift in all of the places before it gets into the model, but also what comes out of the model can change, because usually what comes into the model has also changed. So all of this stuff. But basically, data drift or concept drift, label drift, covariate drift, which is both of them happening at the same time, they're all something that basically happen when the shape, let's say it's called the shape of the data, has kind of changed over time. So how do you detect it? Well, in this particular example, we're taking this scenario of you've done something, you've validated everything works well at training or development time, and you've put your model into production. What you in general want to be doing is something that goes along this sort of simple scenario, right? You have your model's data around training time. You know what it looks like, or you want to make sure that you know what it looks like in one way, shape, or form. So you want to sort of freeze a reference distribution, perhaps, right? Kind of capture something that tells you this data looks like this at time n. So my order price in that example is normally distributed with a mean of 500. Okay, and then you want to use that reference distribution perhaps as you go. Every day, every week, like however many times you might want to peek into the quality of your data, and then you basically say, well, is the distribution of this feature or set of features today still looking like what it used to look like at the time I knew it looked good? Does that sort of make sense? In principle, that's pretty simple. You end up doing basically, you end up probably saving some kind of histogram, maybe, or some kind of probability density function that you can use to sort of remember that, or you end up maybe capturing a sample of data and push it into like a storage place like S3 or whatever, and then you have some automation that goes in, checks the data now, compares it to this using very standard distribution comparison methods such as like Kolmogorov-Smirnov test, chi-squares, Earth mover distance, PSI. Like there is a flurry of algorithms. They all have their assumptions and their quirks, and that's fine. But the idea is that, right? And it's simple in principle. It's not like, if you can build your recommendation model or your prediction of everything model, you can definitely implement those. But you implementing those still results in writing a bunch of stuff for it. So that brings me to the importance of a data quality framework, whichever it is. I happen to work for Soda, so I'll talk about something, but intrinsically, you should not ask of your teams or data teams to necessarily focus on building that, especially for teams that don't have this capacity in-house, right? Like a lot of teams are small, and in some organizations, you want to have a team that's going to give you value. Maybe you don't necessarily have a staff of ML ops engineers or data engineers that can build you a platform for this. I happen to be working in a team where we ended up re-implementing yet another framework because the frameworks at the time weren't so good. But that's basically, nowadays there are frameworks out there. You should probably use one. So and that's kind of what I wanted to. This kind of what I alluded to is that it's simply put, it's you just have to write a lot more code, right? You have to first of all think about, what are the methods that we can use for this particular problem? That's a little bit of research. Luckily, the internet is there. Then you have to orchestrate the checks, like when do you run them? How often do you run them? Where, okay, do I put it as the code of the ML model, like we saw, for example, like so with the talk earlier, like so is it that? Is it something that runs in parallel kind of every now and then? All of these kind of decisions you have to make, and you have to potentially write something to orchestrate it. Then you have to think about, okay, well, I don't want to write this specifically for every model. Maybe I start to want to make it reusable. Then you're already writing yet another framework. The list goes on, right? So that's why I'm saying it's hard. It's not complicated in general to assert quality of data, at least for 80% of the things you want to check. But it is hard to do it as part of your normal life cycle if you don't have a framework, perhaps, or a team that can build you one. So the idea, again, for this thing of use something that allows you to do this is you don't want to add time to your release, right? Like deploying ML automation already takes time and resources. Like your data scientists are already busy doing something very complex and clever, and adding stuff like data quality monitoring on top just makes everything go extra long. And that's where I was saying it ends up on the backlog usually. So wouldn't it be nice if you could ultimately, as you're about to ship your model, or you have had your model in production for a while, do something like this, right? So let's imagine I'm checking my orders table. So this is by the way, this is a piece of DSL of Soda. So I'm gonna present you a feature that we've built. But you'd want to do something like that. It doesn't matter who does it, but we happen to do it pretty well because of that new language that we sort of came up with, which is called Soda CL. Some of you probably heard it around. But it's a way to basically write instructions to get something done. And we've got a built-in for this. This idea is, write do distribution difference on this column of my data sets. Very, small example here, using this reference distribution. We can talk a bit about why the syntax looks like this, and then a sort of score or threshold that you want to look at. Because I'm using a KS test, a Kolmogorov-Smirnov test. This one is always, I'm asserting this thing of if it is above p0, a p-value of 0.05, then I have a problem because the distributions are statistically significantly different. So it's always a bit weird with p-values because it brings you, it makes you double negate a lot. And then we have here like a place where we hold this reference file. We've actually got this way so that you actually can use this without storing data anywhere. You can store descriptor somewhere and have it running entirely out of complex infrastructure. But we'll talk a bit about alternatives to that. So what if you could write this and get this scheduled as part of your pipeline and have this run over time, and then whenever a problem happens, you'll be notified. That'd be ideal. And so this is kind of this is a demo that I will narrate because I don't have a computer here. But I also realize the quality of the font is probably not great. Is it? Can you read stuff? It looks like there has been some compression. So maybe when I press play, things are a little bit better. Are they a bit better? Okay. So I can't really see very much. But so I've basically inserted this normal distribution here. And here I'm generating the reference. So I'm capturing the distribution descriptor at this time. And this ultimately, under the line, just runs a select of your column, maybe with a filter of like a certain date. And you can see here that it generates sort of this file that holds a bunch of bins and a bunch of like histogram values, right? And then what I'm going to do after this is I'm going to run a scan of soda that points to the check file where I defined the distribution difference. And I'm going to run this. Well, it looks like this, by the way. So just what you saw before. So applied on the order price column using this reference file. So I think here I'm going to be running the scan. And in that instance, I ran it on the same data that I generated the reference file, so it passes, okay? So that's all good. Now I'm gonna add a little bit of mess in this data. I'm gonna add or fakely change the distribution to that orange one, doing the same thing. So I'm just putting this data in the database right now, quickly on the left. And then here, I think the word fail should is there. So that's sort of that's demo of the feature, right? The idea is it should be as easy as that, and it can be if you have a tool that allows you to easily define something, use a set of built-ins for this, and a way to abstract away the sort of complex, I have to save my data somewhere. How do I save it? Do I save it as a descriptor? Do I save it in S3? All of that kind of fun stuff. So that's one way of doing it. So what's next? Obviously, so this feature, by the way, is available yesterday. So it's something that we wanted to start. Soda it's been around for a while now, and it's been mainly focused on let's say simpler validation rules with thresholds and stuff like that. And a lot of times we for an ML crowd, sometimes those you would want to leverage, and that's perfectly fine. But stuff that is a bit more complex like this and a few more are a thing that we're sort of veering into. So that's definitely more to come on here. So one of the things that we want to really do, I showed you something that doesn't give you a lot of output. It doesn't even give you like the p-value right now because we just built this and we just want to kind of make it work. But one of the idea is if you were to connect it to our Solo Cloud product, you'd be able to see your distribution plotted in places. But we might also offer this as in the open source tool that we're doing it. And obviously, we want to be able to offer a lot more control over the different algorithms that are used for this. So I used this KS test. For categorical data, you'd use chi-square test, which we have as a built-in. But there is a plethora of methods available out there, and depending on the underlying data that you have for yourself, you might want to be able to control that. So our language will extend to allow users to request specific algorithms, or because the code is open source, implement their own and help us build and extend this kind of thing. Obviously, what I showed you earlier, this approach of saving bins and weights has some problems. I'm sure that the data scientists in here are like, oh, this kind of has some problems, because then you have to recreate your data, from these discretized things. So that's true, and we can talk about this further, like how it works, if you want. But we want to be able to maybe offer a way to, instead of you saving a descriptor to a file, maybe upload a sample of your data into storage, and then we'll take care of getting it wherever it needs to be, and then comparing the data to data rather than data to a reference object. And then obviously, because this is essentially a generic test for different distribution comparison, we want to do something which sort of has convenience wrappers around drift. Like you could say, well, monitor drift on this model on this set of features. Here are some labels, like do your thing, right? Kind of like a just convenience in the language for this to happen. All right. So as I said, it's available and it's all open source. It doesn't even require connecting to our Soda Cloud. It's all able to work for you right now. So you can head over to our docs to find out a bit more, and I'm happy to answer more questions here. You can install it by doing, pip install soda core and the data source type of your whatever data store you have. So for example, if you're using Snowflake, soda core, Snowflake, and then this new package that we started working on, which is this scientific package, is going to have a lot more stuff around distribution, anomaly detection, and time series kind of magic, and all this will be out there. And the Git repo is also there, so if you want to check how it's implemented, if you want to give us feedback on how badly we did it or how well we did it, feel free to do that. And if you want to also contribute to this, it's open source. You can go ahead, and contributing means opening issues is also contributing, by the way. So yeah, and I'll be around. We have a booth, and we are doing an event later today. So if you want to come by, you can do that. And I'll be happy to talk a bit more in details of how we do the thing that we do, whether for distribution or for other types of checks. So thank you very much for listening.